Welcome back to another lesson. We are taking a short detour in our series of finding digits of pi in order to recap on the geometric series. This forms an important link in the last step in our previous lesson. Here we see terms 1 plus 1 over 3 plus 1 over 9, etc., etc. This is the same as 1 plus 1/3 plus 1/3 squared plus 1/3 cubed, etc., etc., as seen in the last line. That can be expressed as a sum s equal to 1 plus r squared plus r cubed, etc., etc. This continues indefinitely, as shown by the last term r to the n, where n can be an arbitrarily large number. Next, multiply both sides by 1 minus r. Some algebra will show the simplified form in the third line. Basically, every term except 1 and r to the n plus 1 will cancel out. The final step is to divide both sides by 1 minus r. That leaves us with an expression for the sum of s in terms of r. Without losing any functionality, we can restrict r to be less than 1 and let n go to infinity. This makes r to the n plus 1 go to 0, which simplifies our expression. S equals 1 over 1 minus r. So that's how we derive the expression to sum a geometric series. How about some examples to see how it works? Back to this guy. We have identified r is equal to 1/3. Plug that in for r, and the sum s equals 3/2. Numerically, that looks like this. 1.49999 is very close to 1.5, which is the decimal form of 3/2. Does this table of data help convince you? Those were numbers, but we can plug in variables to the same expression, as we did in the previous lesson. Here's a reminder of that. R is equal to negative t squared. Plug that into the geometric series, simplify, integrate term by term, evaluate at t equals x and t equals 0. That leaves us with this series expansion in the last line. In case the last slide was too busy to understand, take a look at this instead. R is equal to negative t squared. Plug that into the geometric series and simplify. All that remains is to integrate both sides. The right-hand side can be integrated term by term. That's exactly what we're doing here. Then we evaluate at t equals x and t equals 0. This connection is more thoroughly explained in the last lesson. Basically, we're showing that inverse tangent is equal to this series expansion. How about another example of the geometric series with some numbers? This time we start at 10 instead of 1. How do we handle that? Very similarly as before. Find our ratio first. R equals 1/5. Plug that in. The only difference is that we multiply everything by 10 to scale it up. That leaves us with 12.5 as our final answer. In case you needed some convincing, here is more evidence. The third column shows the numbers we want to add up. 10 plus 2 plus 0.4 plus 0.08 and on and on and on to infinity. In the last column, we add those up. It seems to be converging. 12.499999 is awfully close to 12.5. I'm convinced. How about you? Those were all infinite summations. What about a finite sum? To tackle this, we find two infinite sums and subtract the smaller from the larger. The ratio r in this case is 1/2. Plug that in and multiply by 384, the largest term in our sequence. We do the same thing for s2, except we multiply by 3. Why 3? Because it is the product of r and the smallest term in our sequence. 1/2 times 6 equals 3. Subtract s2 from s1. We get 762. That is the same as if we just added 6 plus 12 plus 24 plus 48 plus 96 plus 192 plus 384. In fact, that probably would have been easier. But this approach of using the geometric series would be helpful if we had more than 7 terms in our summation. Well, that was a quick refresher on the geometric series. Next, we'll be getting back into estimating pi with an infinite series. Feel free to ask questions in the comment section below. I appreciate your support and look forward to seeing you again.